This is a lecture primarily about solution stoichiometry, but toward the end I'm also going to discuss some aspects of what makes certain things soluble while other things are not, in preparation for reviewing reactions in solution. All right, so to kind of boil solution stoichiometry down to the most important aspect, do you remember the equation for molarity? It's molarity equals moles of solute over liters of solution. And if we rearrange that, we know that moles then equals molarity times volume. And the reason that's important is with any stoichiometric calculation, it's almost always you're going to go to moles first before you do anything else. And so it's handy, it's critical actually to remember that how you find moles in solution is by multiplying the volume times the molarity. And you can see by doing that, liters cancel and you get moles. So the three kind of basic steps you're going to be going through in almost any molarity calculation is shown right here generically, okay? So typically, if you read a question, you will be given the volume and the molarity of a particular substance in the chemical reaction. So you're going to start out by multiplying those two together. They get the moles of substance. We'll call it substance A. Once you have the substance in moles, you can use a mole ratio, just like we always do in stoichiometry, to convert from one substance to a different substance, in this case, B. Notice now, if you haven't worked with molarity that much, molarity, of course, is moles per liter. So anytime you see moles per liter kind of in a fraction like this, we're using it as a conversion factor, okay, to convert between liters and moles of that substance. All right, so once you have moles of the other substance, you're just going to have to read the question to see what they're asking for. Are they asking for volume of that new substance, or are they asking for molarity of that new substance? So the question, this third step here is going to vary, but let's just say they were asking for volume of B. So what you would do is you would take the moles that you just calculated for B, and then multiply by the molarity of B, which they'd have to give you if they're asking for volume. In this case, you'd have to put molarity upside down, 1 over molarity, so that the units cancel on the diagonal, and then finally you would have volume. So let's look at an actual problem. All right, so this problem is asking for volume, just like we did, of a 0.150 molar potassium chloride solution. And you can see the reaction shown here. Okay, and it is reacting with a 0.150 liters of a 0.175 molar lead to nitrate solution. All right, so I think if you haven't worked with this type of solution stoichiometry before, it can get kind of overwhelming. I mean, let's face it, there are 3 numbers, 4 substances. So what I tell my students is kind of an easy way to start. Look for information, 2 pieces of information about the same substance. So for example, lead to nitrate, they give us both the volume and the molarity of it, okay? And that'll always be the case in these solution stoichiometry. So start with the substance that has the most information, quantitative information given about it. So here we go. We're going to start with, I just pressed something by accident. Okay, there we go. We're going to start with the 0.150 liters lead nitrate, and then multiply it by the molarity of lead to nitrate. Now notice again, we are using molarity here as a conversion factor from liters of the solution to moles of the solution. All right, so now at this point, if we were to stop, the units would be moles of lead 2 nitrate. So now we can use our mole ratio from the balanced equation. Make sure that you have the right thing in the numerator and denominator. So lead nitrate has to be in the denominator so that it cancels out. And if we look at the balanced equation, there's 1 lead nitrate for every 2 KCl. And so here's our mole ratio. And finally, since the problem is asking us for volume of KCl, at this point we have moles of KCl. We're going to use the molarity of KCl, which was given, as a conversion factor again. But this time it's going to be upside down because we need to have moles of KCl on the bottom and liters on top. So here's a 3-step calculation, solution stoichiometry, and gives us 0.350 liters of KCl. So in really abbreviated form, we're going to say that solution stoichiometry starts with liters of substance A, uses molarity to convert to moles of substance A, and then uses mole fraction to convert to moles of substance B, and then can if this is what they're asking, using molarity of B to get to liters of B. Alrighty, here's one for you to try. Follow the format on the last slide. This problem, I'll give you a hint, this problem's asking for a little bit different. Instead of asking for liters of a substance, they're asking for concentration of a substance. So that's going to change the third step you do. And when it says concentration, of course, they mean molarity or moles per liter. So that's my hint. Remember that molarity is moles per liter. And so I would turn the video off and come back after you've given it a shot. All right, so I'll just work this out right here. Again, you are going to look for the substance that has the most quantitative information given about it. And that is right here, sodium hydroxide, 14.9 milliliters. They give you the volume, and 0.978 molarity. Okay, so we're all set. We are going to begin with NaOH because that's the most information. Okay, so I'm going to go ahead and convert the 14.9 milliliters to liters. So I'm just going to do that in my head. But remember that the conversion factor is 1,000 milliliters equals 1 liter. All right, so 0.0149 liters of sodium hydroxide. I'm going to use molarity as my conversion factor. And I have to have liters down here. So 0.978 moles in 1 liter. That's what 0.978 molar stands for. Okay, so liters cancels. Okay, and at this point, I have moles of NaOH. Is 0.01457, and that is moles of NaOH. Now, you don't have to solve it in separate steps. I'm just doing it now to make it more apparent what I'm doing. Okay, so now I'm going to take that 0.01457 moles of sodium hydroxide. Now that it's in moles, I can use mole ratio to convert it. And I'm going to write the balanced reaction up here because you may not know how to write these reactions out yet. So just in case. It's an acid-base reaction. You get water and salt. Okay, but the point is, looking at the stoichiometry, it's a 1-to-1 to 1-to-1 mole ratio. So that means that for every 1 mole of sodium hydroxide that's used, there's also 1 mole of HCl that is used. So we have the same number of moles of HCl as we do NaOH. Oops, what happened there? Okay. All right. Now, this is normally where we would take the moles of HCl and multiply it by the upside down molarity to get volume. This problem didn't ask for volume. What did it ask for? It asked for concentration or molarity of HCl. So, molarity, what is molarity? It is moles over liter. You just calculated moles, and guess what? We have liters right here. So there's 25 milliliters of the HCl acid. I'm going to go ahead and convert that to liters, okay, because that's what molarity is, molarity moles per liter. So if we take the moles that we just calculated and divide that, here, let me just rewrite it over here. Moles divided by 0.025 liters, and let's see what that gives us. That gives us a molarity of 0.583 for the HCl. So the correct answer was B. Alrighty, I'm going to switch gears a little bit, and I'm going to talk about some conceptual ideas, kind of set you up for going into aqueous chemical reactions. And the question I'm going to ask you is, why do some things dissolve in water and other things don't dissolve? What's going on? Well, hopefully you've learned a little bit about intermolecular attractions between substances, because that's the key. And this last little statement here is the most important statement on this slide. And it says that if the attraction between the solvent and the solute is strong enough, and as a matter of fact, stronger than the attraction between solute molecules themselves and between solvent molecules themselves, then it will dissolve. So the bottom line is the attraction between the solvent and solute must be very strong, okay? Because it's got to essentially break apart or separate the solute molecules, and the solvent molecules become disrupted too. So these attractions have to be super strong. So let's think about salt. We know that salt, table salt, NaCl, dissolves in water pretty readily, right? So what's going on? Well, that means, what that tells us is that the attraction between water molecules and the individual ions of sodium chloride are stronger than the attraction between the cation and anions, and also between two different water molecules. That's pretty amazing. So there's an image in a slide or two that'll let you see why that is more so. So what happens if you envision that here's a solid chunk of sodium chloride with its cations and anions, as it starts to dissolve, the individual ions kind of float off into solution, but look what happens to them. They get completely surrounded by water molecules, and we call that solvation, when a solute particle is totally encaged, surrounded, and stabilized by the solvent. And of course, here the anions are also getting completely solvated. And so this intense attraction between multiple water molecules and the individual ions is what makes it soluble. All right, so a little bit of vocabulary. Again, this is setting you up for the first reaction we're going to learn about in aqueous solution is our precipitation reactions. So electrolyte and non-electrolyte. I have learned that students, this tends to go in one ear and out the other, but it's really very, very simple. An electrolyte is simply something that conducts electricity. And a non-electrolyte, something that does not conduct electricity. Okay, so here's your little image, okay? And here's a non-conductor, doesn't light up a light bulb. All right, why? What makes an electrolyte? It turns out that in order to conduct electricity, I'm not sure if you remember, but electricity is simply the flow of electrons. Okay, so anything that conducts electricity must be able to interact with those electrons and, in fact, move them around. And it turns out that you have to have freely moving charged particles, ions, in order to conduct electricity in a solution. And so inside this solution, we have sodium cations, chloride anions, and so as electricity enters, the chlorine or the anions are going to repel the electrons, and the cations are going to attract the electrons. But in any case, the ions will interact with the electrons of the electricity and allow them to move through the solution. So it will conduct electricity. If you have a solution that is not made up of an ionic solute, so it has no ions in it, sugar's a really good example. So glucose sugar is C6H12O6. That is a covalently bonded molecule. Okay, no ions in it. And so it's not going to separate into anything when it dissolves. It's going to just stay as a glucose globule when it dissolves. And so there are no freely moving ions interact with electricity. So solutions of any covalently bonded compound, there are a couple exceptions, but I'm going to make a blanket statement now, are non-conductors or non-electrolytes. Okay? And that's true for virtually all covalently bonded compounds. Alrighty, this is a really good image. So, as I said before, any ionic compound that dissolves in water is going to have freely moving cations and anions dispersed throughout the solution that are going to interact and allow for electricity to flow. Sugar, here is kind of a model of it. Since they're covalent bonds, it's just going to remain intact. It still dissolves in water, we know sugar does, but it's not going to separate into ions, okay? And so there are no freely moving charged particles, therefore this is a non-electrolyte, non-conductor of electricity. All right, so an example, or how do you determine whether something's an electrolyte or not? All soluble ionic compounds, and if you haven't seen ionic solubility chart yet, that's something you'll have to get real familiar with pretty quickly. So any ionic compound that dissolves will dissociate into the ions and therefore will be a strong electrolyte. And in general, the more ions you have in solution, the stronger the electrolyte, the more electricity it conducts. So even if I dumped in more and more of the calcium chloride, it would become a stronger and stronger electrolyte. Now, I did say that covalently bonded compounds make non-electrolytes. The exception to that are strong acids and strong bases. Strong acids and strong bases, well, that's ionic. Strong acids, okay, even though they're covalently bonded, will ionize in aqueous solution to give you the hydrogen ion and then the conjugate base. And so strong acids have freely moving ions too and are considered strong electrolytes also. Weak electrolytes, we can go over that a bit later, but there is such a thing as a weak acid. It ionizes a little, but most of the molecules of the weak acid will stay intact and not form ions. But because you do have some ions present, it's going to conduct a little bit of electricity. And then, of course, covalently bonded or molecular compounds that dissolve in water, if they're not a strong acid, they're just non-electrolytes. All right, so now that we know something about the theory of why something dissolves and what it does when it dissolves, let's talk a bit about how we determine like what ionic compounds dissolve and what ones don't. And so there is a chart which most professors want you to commit to memory, at least the more common ones. And that, again, that'll become very important when we start talking about chemical reactions in aqueous solution. And here it is. These are the solubility rules, and I recommend to my students that they print them out, start working with them on sample practice problems, and you'll probably commit them to memory on your own if you work enough problems. So I'm going to show you how to use this table. In the upper left quadrant, we have substances that are soluble. Okay, so the most important by far of probably any of these rules is if you have a group 1 metal as the cation in any ionic compound, it will be soluble. Always, no exceptions. Okay? It's also true if the ammonium ion is the cation. So things like lithium chloride, sodium iodide, ammonium bromide, those things are all soluble. So if you're looking at something trying to decide if it's soluble or not, if you see that the metal's from group 1A, it is soluble, period. All right, so then there are some anions that pretty much always render an ionic compound soluble. If you are rusty on your polyatomic ion names and charges, you'll want to review those. So nitrates, NO3 minus, and acetates make an ionic compound soluble. Always, 100% of the time, no exceptions. So what would that be, for example? So if we have calcium nitrate, okay, it is a nitrate, so it's soluble. If we have magnesium acetate, okay, that is soluble because it has acetate. There aren't any exceptions. All right, so now we get into ones that have some exceptions. If a halide is the anion in an ionic compound, so again, it could be magnesium chloride, calcium bromide, okay. These are soluble. In fact, most halide-containing ionic compounds are soluble, but there are some exceptions. If the cation with the halide is silver, mercury, or lead, the compound is insoluble. And in general, silver, mercury, and lead are kind of troublemakers. A lot of times they make an ionic compound insoluble, so that's kind of just a good thing to remember. Notice also that fluoride is not in this usually soluble group. All right, so finally, the last anion that tends to make ionic compounds soluble are sulfates. And the key exceptions of those, you have lead and silver again, but the most common exceptions by far are the heavier group 2A metals. So if you look at group 2A at the bottom, strontium and barium, those make any sulfate insoluble. So for example, let's see. So barium sulfate would be insoluble. And remember we show insoluble with an S. Strontium sulfate would be insoluble. But if you go farther up to, let's say, like magnesium sulfate, that is soluble. So you'd put aqueous, right? So the lower left quadrant shows the compounds that tend to be insoluble. So if the anion is a hydroxide, sulfide, carbonate, or phosphate, they are almost always insoluble. There are some exceptions. The most important being, remember that if any ionic compound has a group 1A metal is the cation, they are automatically soluble. All right, so again, I would print that out so it's handy for you to use and practice with. Here are some examples, and I would recommend turning off the video for a minute, seeing if you can figure out, looking at the chart, whether or not these are soluble. All right, so this is what I do. I'm like, okay, my chart says something about chlorides. It says they're usually soluble, but there are some exceptions. And then I ask myself, is lead an exception? Oop, yep, it is. So this is insoluble. All right, again, chlorides are usually soluble. And then is copper one of the exceptions? No. All right, so that is soluble. Nitrate, I remember that. Nitrates are always soluble. Here we go. Now, sulfates are usually soluble, but there are some exceptions. And the more common exceptions would be barium and strontium. So that, again, is not soluble because of the barium there.